Good morning, everyone. I'm very glad to have this opportunity to present some of our research results. This is a joint work with Dr. He. I use RANS data, but I'm a statistician, so I focus on the methodology. I will talk about the problem we have and the proposed methodology we use. Then I focus on the application, so it's from RANS data, and then have some conclusion. How to compare different regression models, such as a linear model, non-parametric regression, support vector regression. We can use the goodness of fit test, lack of fit test, or just focus on the prediction errors. So people split the data and then training data, build a model, test the data, measure the prediction errors. Do we need multiple training testing sets? So in the end, I'll give you the conclusion. So there's a statistical result to support we should use multiple training and the testing set. Just one random split is not good enough. So RANS data, just like all other surveys, there's the number of potential predictors can be quite large. Machine learning method may be a good tool. Can we use variable reduction or ensemble method to improve the performance of support vector regression? So this is two methods we proposed. One is the reduced version, the other one is the ensemble version. I will discuss more details. So first we talk about the repeated learning testing procedure. So the idea is you randomly select multiple splits, create k different splits and save to k different files. And then each time you read in the split, and then you use the same training data, fit all the models. If you want to compare all different models, then you build our models on the same training data, and then you do prediction on the same testing data, and then you record the results to the output file. And in the end, then you use statistical tools to analyze the results. Okay, so this is what we have done. And you can use simple random sampling, you can use stratified sampling. In this project, we use simple random sampling. Yeah, in another project, I use stratified random sampling. This algorithm, repeated learning testing, first proposed, introduced by Bremen in 1984. And this is an approximation of leave P out. So this all the properties in South's 1993 paper. And we use the parallel computing, request the k over 10 processes, and then let each process do the computation for 10 splits simultaneously. So computation is a problem because this is a machine learning approach. There's different ways to measure prediction errors. So we use average squared deviation on the testing set. You can use anything you like. Here's some simple example for hypothesis testing. So we compare two models. One is a linear model. Model one is a linear model. Model two is a non-parametric regression model. You can use support vector regression to estimate this one. You don't need a linearity assumption. So, and for each split, so you build a model one, model two on the same training set. And then you compute the prediction error on the testing set. And then if prediction error of model one is smaller, then you count one. Okay, so then we define P is the proportion of all possible splits where prediction error of model one is smaller. Okay. And based on that, so I remove all the theorems from the slides. Okay, so basically, so if we try k equals 100, given significant level 0.05, so you only need to count how many times the model one has smaller prediction error. So if this R is less than 42, So you find evidence against the null hypothesis. So linear assumption is not appropriate. So this is a binomial test. And similarly, you can do the paired t-test. So you can define the prediction error improvement. So you have a model 1, model 2. So prediction error, the difference we call it prediction error improvement. And this is measured on the ice spirit. And then you reject the null hypothesis if the confidence interval for the true prediction error improvement is positive. Okay, so you can use both statistical tools to do hypothesis testing. We propose H-step reduced support vector regression. So H equals 1 to up to D minus 1. D is the number of predictors in the data. So basically you just remove H equals 1. That just means you randomly remove one of variables. H equals 2, you can remove 1 or 2 predictor variable from data. And then we use algorithm try to find the best model. So the other method we propose is called ensemble support vector regression. So for this case, we just average all these possible models. Okay, let's focus on the example. Sorry. Yeah, so the data is from range 1 data. So we have 68 predictor variables, and the response variable is the body mass index. Total number of observations is 2,304. And we did 100 random splits, and we try 2 different split ratio, 80% for training, 20% for testing. And another case is 90% training, 10% testing. In this talk, we focus on the first case, 80% training, 20% testing. We compare 5 models, full model, just all the predictor variable into model, linear model, and then reduced model, we use AIC select features. And also we use support vector regression based on AIC select features. On average, there's 31 variables selected by AIC criteria. And also we have proposed to modify the support vector regression models. We only consider 1 step. That just means randomly remove one of predictor variables. And here's the result from the binomial test. So you can see, so 95% confidence level, we only need to compare to 58. So first row, you can see all models better than full model. That just means variable selection is important. So if you do, because there are too many features, you do feature selection, you get the better model. And the last column, you can see all these values bigger than 58. So ensemble support vector regression actually is better than all other methods. Because we have too many features in general in these surveys, and you want to build a model, you should do a variable selection, and you should not expect that there's a best model exists. No, there's no. So ensemble support vector regression is better than all others. So this is very clear. Yes. Yes. We also look at the paired t-test. We report this prediction error improvement, and all the findings are similar to previous one. In this case, so there's no contradiction. But for other cases, it could be there's a contradiction, because binomial test tells you which method is better. And here, paired t-test tells you the magnitude of improvement. Okay, so we also did some statistical mixed model. We try to decompose the variation in the results. Random splits account for 97% of total variability, which indicates the importance of multiple splits instead of 1 split. So if any result based on one split, so more likely misleading. So so you need to do multiple splits. Also, the general framework can also be extended to compare models for other problems like a classification problem, like not just the regression problems. Okay, that's all. Thank you.